On this edition of Chicago Tomorrow, a tiny silicon chip may provide new hope for some forms of blindness.
Hello and welcome. I'm Aaron Freeman and welcome to Chicago Tomorrow. Each week we report on promising scientific, technological, and medical breakthroughs right here in Chicago.
And tonight we focus on science and technology. We'll look first at a tiny silicone chip implant that may eventually help those with a degenerative eye disease regain some of their sight. Here to tell us about it is technology correspondent Chris Hammond.
Elizabeth, it's an amazing story about a promising new device invented by two brothers, one an ophthalmologist and the other an engineer. Together they developed a prototype of a tiny device that may in the future provide some degree of sight to those who suffer from retinal disease. Our story is about a vision of the future.
Approximately 30 million people in the industrialized world suffer from retinal diseases which cause blindness, and there has never been a treatment. Until now. Here in Chicago, an ophthalmologist and an engineer, brothers Alan and Vincent Chow, have developed a radical technique using artificial retinas, which they hope will restore sight. I went to their suburban Chicago lab to find out how their vision of the future may help people see.
We've implanted the first artificial silicon retinas into the eyes of 3 patients who are blind from conditions called retinitis pigmentosa. So this is the first time that this has been done in the world.
In what sense artificial? I mean, what's it made out of?
Well, these devices are made of silicon. The silicon chips that are approximately 2 millimeters in diameter, and about 1/1000th of an inch thick. In other words, about the thickness of a human hair. And on the surface are thousands of microscopic solar cells, or what's called microphotodiodes. And the purpose of these is to stimulate the remaining retinal cells to induce perhaps a visual signal.
When people hear silicon and chip, they think of computer chips, but that's not what this is it?
It's similar. It's based on the same type of fabrication process that's used for computer chips, but instead of fabricating a microprocessor, we fabricate solar cells on these structures.
Okay. So essentially the same sort of thing that's on people's rooftops who are getting solar energy. You've miniaturized and are putting in people's eyes.
It's related to those structures, but quite a bit more sophisticated, as you can imagine. They're some of the smallest solar cell devices ever fabricated, and instead of requiring wires to lead off the structure, they actually have electrodes built in on the solar cell. And the light actually travels through the top electrode to the actual solar cell, and then the current is brought out through the electrode, which then stimulates the retina. And so the first time we made these, the people we went to would always ask us, well, where are the wires? Well, there are no wires. Much of the surgery is actually quite routine. This involves making an opening through a relatively bloodless portion of the eye so we could enter the inside of the eye. We then make an opening into the portion of the retina where we plan to put the chip, and then the chip is placed through this opening into the pocket, and then the retina is smoothed over the implant.
And have you got results back yet on sort of the effectiveness of the surgery, the effectiveness of the technique?
Well, what we've been able to demonstrate first is that the surgery is feasible. Second, we found that there's no rejection, there's no infection, no inflammation, and the chip stays in place. And I'm sure everyone is wondering, well, what is the patient seeing? Well, right now we're evaluating the data and the information that we get from the patients.
I know that the one thing you don't want to hear is anybody saying that what you've done is cured blindness. Where do you see yourself in terms of the steps along that path, though?
What we've done so far with the implantation in the first 3 patients is really just the first step in this process of trying to find a way to improve just vision, improve visual function. It's not a cure. It's certainly not a cure. It's a way to recover some visual use to these patients who really just can't see.
I asked Vincent Chow, the engineer, to show me how the chip works.
So we take the solar cell structure, and it has the ability to produce some very small voltages upon being struck by light. and we implant it into the eye at a point where doctors know that the visionary process begins as a very mild graded voltage. The rest of the cellular layer takes this analog voltage and actually converts it into a digital data stream. Nature a long time ago knew that it was long distance communication between the eye and the brain, and so it's all digital from the time it arrives on the nerve fiber layer and reaches the optic nerve into the brain.
I asked Dr. Vincent Chow to describe the process of discovery that yielded this simple device.
The artificial silicon retina is really an integration of two sciences that up to this point have been quite far apart. Semiconductor processing, fabrication, computer chip type work, and medicine. And fortunately, I was in a position where I have access to these skills because everybody in my family is an engineer. And except for myself, I think some have called me the black sheep of the family.
There's a sense in which it feels like it occurred to you could tinker, that you could look at the eye, look at its function, and think of it as a device that is broken, and you were looking for ways to fix that device. I mean, that's the way. As I listen to you, that's what it sounds like.
Yes. Well, the eye, even though it's a biological structure, actually is similar to a very sophisticated video camera. So once we understood relatively clearly how the eye works from an electrical standpoint and understood its circuitry, then we could say, yes, is this something that can interface with a semiconductor electrical device?
Finally, I asked the Chows to speculate about the potential future uses of this technology. If these devices can receive light, could they be used to receive other input and create virtual realities?
Well, once you have a device in the retina that's able to transduce light into electric signals, which is what the artificial silicon retina does, or the ASR chip does, you can envision all forms of programming that can be done with light to create the kind of electric signal that you want.
Because just like any electronic device, if you can make sound, you can produce anything you want, from a stereo system music to voice to artificial speech. They're all basically transducers into sound. Here we're looking at a transducer of light into a stimulation that the brain can successfully understand. And with that transduction layer achieved, truly you can be your own painter.
It's important to note that this work, while revolutionary, is not a cure. Instead, it represents the first step in a long process of developing an engineering solution to a very human problem. What is crucial here is that the process hinges on a specific point of view from which the human visual system is thought of as a machine that, once broken, can be repaired, re-engineered, and ultimately improved. The results aren't quite in on this particular repair, but we'll continue to track the outcome in the future.